Just to introduce my research, I'm looking at therapeutic tape and how it affects both pain and muscle function, and so I set out to use tensiomyography for the pain element of my research over the 3 to 4 years. So when I started, I got given the tensiomyography equipment and I didn't know how to use it. I just knew that I had to use it because I was told to. And so when I went through the training, there was a lot of variation in that we've seen where you can place the probes, how exactly to place them, what times to use in between consecutive stimulations, and this was evident in the literature as well. So I started by just doing a look-see really to see what effect these parameters would have on my results on my therapeutic tape, because I wanted to make sure that any effect that I did see was due to my tape and not due to the measure protocol that I was using. So the investigation was to look at how stimulus amplitude, inter-electrode distance and interstimulus interval had on maximum displacement and muscle contraction. And we've seen earlier today that DM and TC, which are displacement and contraction time, are the two measures that we do use most commonly. So this is why I've used them here. Again, already seen this, so how it works, just a reminder. So it is just measuring muscle displacement ultimately, and then from its displacement we can look at contraction time. So you place the probe at the muscle belly and you compress it into the muscle, and when the muscle contracts radially, moves the probe, and then we can measure the time of that contraction. And this is a typical output. So you're looking here at displacement in millimeters on the y-axis and time on the x-axis, and I'm interested in maximum displacement, which you can see at the top, and then contraction time. And the contraction time is calculated at 10% of maximum contraction to 90% of maximum contraction. So my research, the aim was 3-part. So first of all, I wanted to look at if the amplitude required to achieve maximum contraction changed if I did this multiple times. So in a lot of the intervention studies, you're looking at a baseline score, then you're giving an intervention, whether it's tape or running, and then you're going to measure afterwards as well, or during the intervention if you can do so. So I wanted to see that if I got to maximum contraction before and after and I saw an effect, is it my tape or is it just the repeatability of the technique? And I was looking at the coefficient of variation between the amplitude required 3 times within an hour to get to maximum contraction. So in a wordy version, there we go. The next part was to look at inter-electrode distance. So I wanted to vary the distance between the electrodes on the rectus femoris and see if it had any effect on displacement and contraction time. And then likewise with the interstimulus interval time, again I'm going to vary the time between consecutive stimulations and see if it affects displacement and contraction time. So this is the method for the first study. So this is the one where we're looking at the amplitude required to achieve maximum contraction. You can see here, this is one block. So I did do stimulations before 40 milliamps. I actually started at 20, but here I've just put on 40. And I stimulate every minute, so I'm leaving a really long interstimulus interval between consecutive stimulations here. And then a nice washout period in between. So I'm stopping anywhere in here when I'm getting to maximum displacement, giving the washout period and repeating the whole process. Okay, so here are the results. So we've got an N of 10 in each group. And so each row is a different participant, and each column is each round of the getting to maximum contraction. So, for example, with the first participant, they got to maximum muscle contraction at 60 milliamps. Then we've got the mean standard deviation of this data and the coefficient of variation for each individual. And the mean for all of this data here is that we've got a coefficient of variation of 5.7%, which is considered low. So that's good. The next study is looking at inter-electrode distance. So we've, in this circumstance, kept the stimulation amplitude the same all the way through. We've got big washout periods here. So I should say in the literature, most people are using between 10 and 15 seconds between stimulations. So 2 minutes is quite big. And then we've looked at 5 centimetres, 7, 9 and 11 centimetres. So it should be said that in all cases, all of the participants received every single condition in this order. So we started at 5 and ended at 11. And this is what we found. So here we're looking at displacement versus intraelectrode distance. And each line is an individual participant, and the solid line here is the mean information. And we saw that there was a significant effect on displacement between 5 centimetres and 7 centimetres, which if I hadn't done this and I was using an eyeball technique just to get to the muscle belly to stimulate the muscle, that could have shown up as a significant effect for my therapeutic tape. So that was quite important within my research to know. So the final study was the effect of interstimulus time on displacement and contraction time. So in this scenario, we're looking at 30 seconds, 10 seconds and 5 seconds. And again, everybody got all conditions. And we've got 10 repeated measures with the specific interstimulus time. And a nice washout period in between the two as well. And this is what we found. So here we're looking at displacement versus interstimulus time. And again, same setup where we've got each line is a different participant and the mean data is here in the solid line. And we found there was a significant effect on displacement when using 10 seconds over 30 seconds, which again, for my research when I'm looking at an intervention is important if I'd been using the 10 seconds, which is quite popular in the research. And then when we also look at how stable the measures are over time, so this is the measure number 1 to 10, and we're looking at contraction time here. And you can see that the most stable interstimulus time over time is 30 seconds. So the major findings from this research is that the mean of the within subject variability for the amplitude required to get to that maximum contraction 3 times within 1 hour, 1 hour is a usual experimental time in our research, is 5.67%. We are getting a stronger muscle contraction when we use 7 centimetres distance between the electrodes compared to 5 centimetres. And we're also getting a stronger muscle contraction. Here I'm talking about muscle displacement when I'm using a 10-second break compared to 30-second break. And that 30 seconds is giving us the most stable result in contraction time over if you're doing a repeated measures experimental design, which is what I often use. We're just going to now pass over to Matthew Harris, who's going to tell you about his research. He's looking at how fat can affect TMG measures. So he's just going to quickly go just 2 or 3 slides just to mention what he's doing. And then I'll come back to future work. There you go. Thank you. I'll stay here actually.
Hi everyone. So yeah, Matthew, I'm currently enrolled on the 1-year master's degree in sports therapy here at Leeds Beckett. As part of our course, we have to undertake a study. When I first sort of came onto the course, we were asked for what ideas we wanted to look at, and to be honest, at the time, wasn't really sure. And it was actually due to talks from Ashley, who's due to talk later on today. He's been doing a lot of work with TMG, and something I had no background on, didn't know what it was, had no experience in using it, and it was only through sort of his enthusiasm and interest in it that sort of piqued my interest basically. So approaching him, we came up with a few ideas, and essentially due to some of the sort of questions you were asking, he knows that there was a gap in the literature with regards to whether the adipose tissue thickness and sort of specifically the fat thickness at certain sites, whether that does have an effect on the TMG outputs. So it's something that he put to me more than I brought to him. but something that we've both looked at since, and we've started from there. So bit of a background on some of the other areas that are sort of relevant. It has been reported that the skin fold thickness in relation to other types of muscle measurement has been shown to have an effect. So both EMG and MMG have had studies published that have shown this, and also relevant to TMG, significant in non-voluntary muscle contraction as well. So obviously that's what we're looking at with TMG. So thought to be a limiting factor, as we sort of alluded to earlier, with the fat layer in the tissue. It's only been sort of hypothesised that it's possibly due to its poor electrical transmission properties and poor blood flow. So it is acting as sort of a barrier for the electrical stimulation from skin surface to muscle. And as I alluded to, there's nothing currently published. There was an abstract of a paper which we found, but it hadn't been published as a paper. We believe it might have been presented. So unless something's come out very recently, which I haven't seen yet, I'm not sure if either of you know of anything that's currently looking at it. So currently still in the middle of my study at the moment, so don't have anything to show you today or anything like that, but it's just to give you a bit of an idea of what we are doing. So we are using skin fold calipers. I know that there are more sort of rigorous sort of techniques for measuring the properties of the tissue, but due to ease of access, ease of use, what we had available to us, that's what we've decided to go with. And as I'll allude to at the end, it's possible that if anything is found, then obviously more sort of rigorous methods, ultrasound, things like that, or MRI, probably more accurate measurements, that possibly that's something that can be looked at in the future. We're using 30 participants in total, 15 of male and female. Predominantly, I think a lot of the research that's already out has been done in male. It's included more males, possibly due to the sports that it's been used in. A lot of studies have been done in football, obviously more male-dominated sport, but as TMG is going to be hopefully increasing in its use, we wanted to include both so that our research is hopefully more transferable to anyone using it, either in testing or future studies. So we chose the two sites are glute max, and we're doing both medial and lateral gastroc. The two muscles have been chosen due to their respective differences in anatomical adipose tissue thickness and fat distribution. So currently we're at 8 participants that have been tested. There are more who have agreed to take part that we haven't tested yet, but we are still recruiting as well. And at the end, obviously, we aim to hopefully add to the literature, provide some sort of valuable contribution, which, as I say, although skin fold calipers may not be the most rigorous form of testing, it's hopefully going to then produce something that maybe people will take on in future, maybe look at more in depth. So fortunately nothing really to show you. It's too early to we haven't really looked at any correlations or anything like that to possibly suggest what might be happening, but hopefully this time, sort of next year or any future conferences, we might have some valuable findings to report to you, and we're hoping that it might be published also, so if you don't research it, then we might be able to publish it rather than present it to you. That's it really. Thank you.
Just wanted to add in the future work that, just go back, sorry. Just to add in, because some work that we're doing after this. Okay, so the future work off the back of this, my study, was that Ash and I are going to be looking at intraelectrode distance on more muscle groups. So we're going to be looking at the biceps brachii, the biceps femoris, gastroc, and the glute max. And again, we're just going to be varying the intraelectrode distance. So that we've got ethical approval for this. We'll be starting probably in September now. And the next study on my PhD will be using tensiomyography to look at the effects of therapeutic tape, which I've already mentioned, on pain and muscle contraction. And this is going to be in a delay onset muscle soreness study. So if anybody wants to participate, please let me know. That would be excellent. So yeah, my thank yous are to my supervisory team. So this is Peter Francis, Dr. Peter Francis and Professor Mark Johnson. And that's definitely the end. Thank you. Any questions? Yeah.
Sorry if I missed it. It's my presentation. What was the population you did the piece of work in?
So it's 10 in each group?
10 in each group.
Yeah.
What were they, how highly trained were they? Recreation active? Or
No. All just healthy participants in this research.
just healthy participants?
Yeah. No caffeine, no exercise that could have produced DOMS. There was quite a vast inclusion criteria, but overall healthy and normal.
Okay. It's nice data and it's useful data. I'm just wondering if the reliability and the coefficient variation, etc., would apply to a more highly trained population where the contractile properties of the muscle are slightly different. I don't know if anyone from TMG can speculate on that. Or
It's hard to say, but probably yes. Because we found so far that, trained athletes react, different to, some sort of activity which is.
Sorry, that's my son who needs to be picked up in Ireland.
So you need to hurry. So yes, to be short. So for some properties you find that for trained people change much differently than for people that are not trained. So I would suggest that there would be some.
and that might influence the
I think so. Yeah.
The point of that I'm trying to get to in my research is for an intervention scientific experiment, people are using it before, during and after intervention. And are we looking at an effect of the equipment, or are we looking at effect of the intervention that we're trying to give for any benefit? And so whatever group you're going to use that intervention in, yes, you'd have to reset normative values, reference values, etc. But as long as your group that you're using are all trained or all untrained, that intervention's not changing. Does that help? Yeah. Sorry?
I have a similar question, but I need to go back to one of your tables.
Mm-hmm.
It was your reliability, I think it was almost the very first table. I noticed there were a number of individuals that had very consistent results,
Mm-hmm.
and then others that didn't.
Yeah.
And it seems to me there's some kind of confounding factor there.
Mm-hmm. Yeah.
And is it possible to go backwards to work that out in some way?
Go backwards in what way?
I don't know, because clearly, like, you can see the first participant, the coefficient of variation. I mean, there's only not that there's any problem with 3 points, but
Mm-hmm.
3 points are just about enough to make a straight line.
Mm-hmm.
That looks quite consistent, and then of
Yep.
course you get to the second and the sixth and the eighth, and it seems to go.
Goes
even
up
though
to
the
20%, yeah.
average-
So it goes up, we've got a range of around 0.06 to around 20, so we've got 19.5% variation. You're correct in that 3 measures is a very low number. That was designed, because it was designed as a look-see, so we're looking at before, during and after. So this is, no, of course.
I'm just curious.
Yeah. So it'd be something that we can build upon from here.
Yeah.
And because our power, we've only got 10 people in each group as well, so that is another massive confounding factor. But 20% is still low. So the range, it is a big range, I agree. So we just need to increase the numbers if we were going to take this forward. And as we are doing, we will be increasing these numbers in Ash and I's study when we're looking at the other muscle groups.
Yeah, I was wondering, would anyone with some experience using TMG be able to speculate why there is some very tight consistency on some, and then others are all over the place?
Is that okay?
Would you know?
Yeah, I think yes. We can only guess.
Yes.
Yeah.
But for example, if let's say the electrodes would lose a little bit the contact with the skin,
They were all fresh electrodes.
Yeah. And as I said,
Yeah.
that would actually affect sometimes. But did you put the electrodes up and down, or you just put them on the muscle and did
In up and down in what way?
You attach the electrodes on the muscle after the first series, and then
No, they were kept in place. During the cycles, the only thing that was the stimulation was turned down to 0, but everything was kept in situ exactly the same for the 3 rounds. Yeah. Yeah.
Nice presentation, by the way.
Thank you.
I'm just wondering, in terms of the variables that you've looked at where you've taken repeated measures, you mentioned that every participant did it in exactly the same order.
Yeah.
So do you think there's any potential there that it's actually an accumulative effect, and if you'd have
Randomise the order.
randomised it,
Yep.
would that have changed the results sort of thing?
Yep. So this is what we're doing. So this is the very first study in my PhD, and now I do randomise the order of everything.
Right.
So yes, there is a systematic bias there, but at the same token, everybody had the exact same protocol. So hopefully it does disappear because everyone's had the same conditions in the same order at the same time to the millisecond I was with that stop clock. So it was, yeah, I agree, future studies, and it's being done now that we randomise the order, yeah.
I mean, and that would be interesting anyway if you do then find that there is,
Yeah.
a bias just based on the
Yeah.
order. That tells you something about the repeated test, isn't it?
Yeah, of course, yeah. Any questions for Matt on the fat study? Not that there's any data yet, but just it would be a good discussion. Yeah. Okay, thank you very much.